Hi class, welcome back to thermodynamics. And this lecture really begins the grand finale of the course. This is what we've been preparing for all semester. And it's really the most exciting part in that we're finally getting to the point where we can evaluate the efficiency of power plants, the energy production of power plants. We're going to look at air standard engine cycles soon. Over the next upcoming lectures, we're going to look at refrigeration cycles. So this is it. This is where the real engineering applications kick in. And so we're going to continue on with isentropic processes. So remember, with isentropic processes, we have the change in entropy, delta S, is 0, or ds dt is 0 if you have a control volume. And isentropic processes are also adiabatic. So you're not exchanging heat with your surroundings, and also now internally reversible. So in order to be internally reversible, right, that's where you don't necessarily have any energy, any entropy production within your system. However, we're going to set this up. We're going to go through some examples, and let's go back to our components of our different larger systems. So turbines we're going to be looking at. We're going to be looking at compressors. And pumps. Nozzles and diffusers. And these are all isentropic devices. Or adiabatic. So let's look at an energy balance here. So we have ds over dt for control volume is equal to the sum over J of Q dot J over TJ. So so this is the heat transfer rate for each component over the boundary temperature for each component, plus the sum for the inputs of the mass flow in, plus the entropy in, minus the sum of over the outlets of m dot out, S out, plus any entropy production for the control volume. Okay, so this is our general energy balance or entropy balance. So this is the entropy balance equation for control volume problems. Okay, so this is for control volumes. So this is the general entropy balance for control volumes. Just like we had an energy balance, general energy rate balance for control volume problems that we looked at a few chapters ago. And so you can simplify this with different assumptions for your system. And one major one, of course, is that if ds dt is 0, this is the steady state assumption. Okay, that there's no change in entropy over time. So that's the steady state assumption in there. And in order to be isentropic, we have steady state and adiabatic, so no exchange of Q, and internally reversible, so no energy production. Entropy production. All right, so let's move forward to isentropic efficiencies. So the isentropic efficiency for a work-producing device, so a work-producing device is when the actual work output relative to the work, so it's the actual work output relative to the work output of an adiabatic device. So a work-producing device, an example of that would be a turbine, where the purpose of a turbine is to produce work done by the system. So the isentropic efficiency of a turbine, which we did talk about briefly last lecture, is going to be equal to the actual work output divided by the isentropic work output. So this would be equal, say, W dot actual over W dot isentropic. That's what that S is for. So another way this can be computed is, since this is a control volume scenario, we'll be looking at enthalpy. So H1 minus H2 divided by H1 minus H2 for an isentropic process. And so the typical isentropic efficiency for a turbine, the typical range is 0.5 is less than the isentropic efficiency. So it's somewhere between 0.5 and 0.9. And so, and that would be for an adiabatic turbine, where you're not getting any energy, any heat exchanges with between the system and the surroundings. And of course, delta KE is equal to delta PE is equal to 0. And we'll look at the condition momentarily where delta KE is not equal to 0. So typically in a jet engine, delta KE will not be equal to 0. But let's move forward now to look at a work-consuming device. And so a work-consuming device takes work done on it. So there's work input. So it's the isentropic work input relative to the actual work input. And so with a work-consuming device, so the more ideal scenario would be for it to be more effective, for it to run it the exact same way on less energy coming in. And so the isentropic work would be the case of less energy coming in compared to the actual, and so that'll give you an efficiency less than 1. So the isentropic efficiency for a compressor, so I'm going to use a C for a compressor, for example, and a compressor is an example of a work-consuming device. A pump is an example of a work-consuming device because you have to put energy into a pump to, say, move water uphill, like to move it from a lower elevation to a higher elevation, like that takes energy in, so work input. So the isentropic efficiency for a work-consuming device like a compressor is going to equal isentropic work input divided by the actual work input. And so this is going to be isentropic in divided by actual in. And so this can also be calculated looking at enthalpy. So it'd be H2S minus H1 over H2 minus H1. And similar to the isentropic efficiency for a turbine, the typical range is between 0.5 and 0.9. So 0.5 is less than eta C is less than 0.9. And that would be for an adiabatic compressor. And of course, we're assuming no kinetic energy or potential energy effects here. And if you're working with a pump, like it really depends on your problem, because the purpose of a pump is to have you're going to have a difference in elevation. But for our power plant examples that we're going to look at very soon, you're not using the pump necessarily in that way. And so we'll look at that. Okay, a thrust producing device is where the actual exit kinetic energy relative to the isentropic exit kinetic energy. Okay, so this is a lot of the cases in, say, a nozzle or in a jet engine. So it's just comparing, you can compare the kinetic energy, or you can compare the velocity squared for the regular process divided by the velocity squared for the isentropic process, which we looked at last lesson. So let's go through an exercise together. And this is number 6.149. And air is at 300 Kelvin, 1 bar. It enters a compressor operating at steady state and is compressed adiabatically to 1.5 bar. The power input is 42 kilojoules per kilogram of air flowing. Employing the ideal gas model with K equal to 1.4 for air, determine the compressor A, the rate of entropy production in kilojoules per Kelvin per kilogram of air flowing, and B, the isentropic compressor efficiency. Ignore kinetic and potential energy effects. So let's write down our givens. And we'll draw out a sketch of the situation. And so we're dealing with a compressor. And we're dealing with air. And we have an adiabatic model that we're applying. And T1 is 300 Kelvin. And we know that P1 is 1 bar. And P2 is 1.5 bar. So we're tasked with finding the rate of entropy production and also the isentropic compressor efficiency, eta C. So let's go through and solve this. And we're looking for this on a mass basis over m dot. All right, so let's start with an energy balance. Because we don't know what T2 is, that would be some helpful information to have. So let's just begin by solving for T2 before we get into our entropy balance to get the entropy production. So starting with an energy balance, we have Q dot minus W dot is equal to M dot H2 minus H1. And on a mass basis, remember we can show this as little q dot minus little w dot is just equal to H2 minus H1 if we want to express that on a mass basis. And for this we have an adiabatic, compression, so the Q is 0. And so we're left with minus W is equal to H2 minus H1. So minus W is equal to H2 minus H1. And remember, we can get H if we know Cp, which we know what our K, so we can find Cp. So it's going to be Cp, the specific heat held at constant pressure, or analyzed at constant pressure, of T2 minus T1. And so then we can go ahead and we can just plug in that, remember, Cp is equal to 1.4 R over, or let's just write it as Kr over 1 minus K minus 1. So W dot, actually let's just go ahead now and solve for T2. So T2 is going to equal H2 C2 is going to equal, T2 is going to equal W dot over Cp plus T1. Okay, so it's going to equal W dot in over Cp plus T1. So Cp is going to be 1.4 times our R for air, which is 0.287 kilojoules per kilogram Kelvin. And then we divide by 1.4 minus 1, which is 0.4, which gives us our Cp is going to be 1.004 kilojoules per kilogram Kelvin. And then the last piece we have is that we have our power input, so that's good. All right, we have everything we need. So T2 is going to be equal to 42 kilojoules per kilogram. And so the kilojoules per kilogram from this W is going to cancel out with the kilojoules per kilogram for the Cp. And we're going to end up with 42 over 1.004. We still have a Kelvin hanging around. And I recommend that when I go through these problems, you go through them too, and you try to make sure the dimensional analysis works out for you. And it's just really good practice to write these out. So don't just watch, write them out. Plus T1, which is 300 Kelvin, which is going to give us 341.8 Kelvin for T2. Okay, so now that we know the second temperature, we can go through and do our entropy balance because entropy is a function of temperature. So this is book 6.149. And this is going to be part B, or no, this is still part A. We're looking for our entropy balance now. And so in steady state, we have 0 is equal to Q over T B plus m dot S1 minus S2 plus our entropy produced for the control volume. So we're looking for the entropy produced on a mass basis. Since this is adiabatic, Q is 0, steady state gives us a 0 here. We want to express this on a mass basis, so we're looking for sigma dot over m dot. So let's set it up this way. Sigma dot CV over m dot is going to be equal to S2 minus S1. All right, well, now we're also dealing with an ideal gas. And so S2 minus S1 for an ideal gas with constant, a constant specific heat for the process, so constant CP, we can use this nifty equation where delta S is equal to CP times the natural log of T2 over T1 minus R times the natural log of P2 over P1. So now we just need to plug in our temperatures. We have our two pressures. We know R, we know CP. We are almost there. So this is going to be equal to 1.004 kilojoules per kilogram Kelvin times the natural log of T2 over T1, which was 341.8 Kelvin divided by 300 Kelvin minus 0.287 gas constant for air kilojoules per kilogram Kelvin times the natural log of P2 over P1, which was 1.5 bar over 1 bar. And this comes out to 0.0146. And since we're on, so the thing is, this is going to be, since this is a rate, it's going to be kilowatts per Kelvin per kilograms per second. So the seconds in kilograms per second and the seconds in kilowatts, which are kilojoules per second, end up canceling. So it makes sense that this is expressed still as kilojoules per kilogram Kelvin. The units make sense, and we're done. Okay, so next we are going to look at vapor power plants. And for vapor power plants, we apply typically the Rankine cycle. So we'll be using the Rankine cycle quite a bit. And there are different types of vapor power plants, but they're functionally doing the same thing. So the goal in a power plant is you want to vaporize some working fluid that you're going to send through a turbine. And I posted a video for you to look at on, we're just going to say hi to a cat for a second because he is playing with my notes. All right, let's keep going. All right, so what was I saying? Yes, I posted a video on how a turbine works. So check that out. It's pretty important for an engineer to know how a turbine works. But you send a working fluid that's typically vaporized in the vapor state, vapor phase, through a turbine, and it turns the turbine, and the turbine's attached to a generator. The turbine turns the generator, and electricity is produced, and it's sent to the grid in real time, right? Because this electricity produced is power, which is kilojoules per second. It's kilowatts. So, for example, it's a rate of energy production, and it's happening in real time. And unless you're able to store it in some kind of battery, you lose it if you don't use it in real time. So there are different types of vapor power plants. You could have a fossil fueled vapor power plant, which I have a teeny diagram down here of a coal fired power plant. And so basically you're just using different energy sources to accomplish turning the turbine, to accomplish vaporizing the fluid and turning the turbine. So often the working fluid is water. And so what you're doing is you're burning coal in a vapor power plant. And by burning coal, you're heating up water that is cycled through. And so that hot water, or the vapor, then is passed through the turbine. And so it's slightly cooler after it comes out of the turbine. But what we do is we further condense that water and we pump it back through as the working fluid that gets reheated. Okay, so it passes through the turbine. Some of the cooled water then is used to cool in the cooling tower, to cool, to go into the cooling tower for the plant. And then the other part, and then the rest of the water is sent back through and recycled here, and is heated back up and vaporized, and it goes on and on. So the difference with these different power plants is what energy source is vaporizing the water. So with a nuclear plant, you're using the vaporization is accomplished via fission reactions. So uranium-235 is typical. Sometimes you'll use 238. Sometimes you'll use thorium or plutonium. It just depends. But there's usually, you have these fission reactions taking place in the core of the nuclear reactor. And what's going on is the heat, the energy produced in that process is being used to heat the water or whatever working fluid that's then vaporized and set as steam through the turbine. So very similar process here. And we'll look at two more very briefly. So another one would be solar. So with vaporization in solar power plants, you usually have solar collectors. So don't confuse solar collectors with solar panels. So with a solar collector, you have a working fluid that is sent through the panels that are heated up. So in this example, we have oil circulated through the solar collectors, and that is heated up. And these plants operate a little differently in that there's also molten salt that is used. So it's the oil is going through and it's heating the salt, which is then the molten salt is being used to heat your working fluid, which is typically water once again, to vaporize the water, creating steam, which is then sent through the turbine, which turns a generator. Then we have water coming out that's used to help, that's cooled in the extent, going by the condenser and then pumped back around. And then lastly, we have geothermal steam from underground. And so you could use wet steam, dry steam. So wet steam just means that it's not 100% vapor, the steam. There's still a water component to it. Dry steam means that you have 100% vapor. Okay, so superheated vapor. And so depending on where you are globally, in some locations like the geysers in California, the geysers is a geothermal power plant in California, and their geothermal gradient, and so that's the increase in temperature of the bedrock as you move deeper and deeper into Earth. And so their geothermal gradient is so steep such that you don't even have to drill very far down, and it gets hot really quickly. And the groundwater is actually in steam form in some locations, like geysers, for example. And so with some geothermal power plants, you can actually take vapor directly from the ground and send it through a turbine, or just heat it up a little bit more. Sometimes there's a vacuum chamber involved, since water boils at a lower temperature under lower pressure. So there are these different schematics, and we're going to be working with these for the rest of the semester. And so this is pretty exciting stuff, because you start to see like, wow, we were looking at all these little components and these little bits and pieces all semester, but now you can see, okay, so this is how it's applied to energy production. Now, like I said, one model for vapor power plants is the Rankine cycle, and this is a reversible cycle, and it's isentropic. So let's go through the Rankine cycle, and I'm going to sketch it out as we talk about it. So from 1 to 2, so process 1 to 2. So let's start at state 1 here. So starting at state 1, we have expansion of the working fluid through a turbine from saturated vapor to condenser pressure. So here we're going through a turbine. So this is our turbine. We have some work output. So this is the power output from the turbine. And let's also draw it as we go on a TS diagram. So that's temperature entropy diagram. And let's stick on our vapor dome, since we're dealing with water. So for state 1, typically we're right here. We're in the saturated vapor portion of our dome. Some processes, we might be out here if we're superheated. So this is another option. I'm just going to call it 1 prime because I'm just talking about the one that I've circled right now. And so coming out at 2, so this is 2, we're going into a condenser. And with a condenser, we have cooling water that's sent through. So we have our cooling water. And we have usually we have some heat exchange going on. So we have some Q dot out here. So that's our condenser, and I'm going to draw it on here. So we're going to be somewhere inside the vapor dome. Typically, if we start out superheated, if we go into this the turbine superheated, sometimes we might end up just at the very edge of the vapor dome for saturated vapor for then step 2. So it just depends. And actually, I'm going to redraw that because these should be at the same temperature, for example. So I'm just going to draw this one right here. And just remember my dots are for if superheated. Okay, so next we come out of the condenser. And so for 2 to 3, we have heat transfer from the working fluid at constant pressure through the condenser and exiting at saturated liquid typically. It just depends. So for 3, we're exiting at saturated liquid. So that's our 3. So let's draw this. So we have 1 to 2 to 3. And then we have our pump. And we have work going in to our pump. And from process 3 to 4, we have isentropic compression in the pump to a compressed liquid. Okay, so here we're at a saturated liquid at 3, and then we go to a compressed liquid for 4. So we're no longer touching the vapor dome. And remember, inside the vapor dome, temperature and pressure are paired. So then what's going on is from 4 to 1, so we're pumping back up, and we're going to go into our boiler. So this is our boiler. And here we have Q going in. All right, so we have heat transfer to the working fluid at constant pressure through the boiler. And so to get back to 1 then, we're going to follow P equals constant, which will bring us to about here. So this line that we're following from 4 to 1, this is P equals constant. And then once we get up to our temperature that matches T1, then of course for P equals constant, T is also going to be constant through the vapor dome. And there you have it. This is the ideal Rankine cycle. So now I know you're super ready to go ahead and go through exercise with me, an example problem. Now this is from chapter 8. We're not covering chapter 7 in your textbook, so don't worry, we didn't skip that far ahead. We're not doing exergy analyses in this class. It's not part of the curriculum. And so for this example, we're looking at a nuclear power plant based on the Rankine cycle that operates with a boiling water reactor to develop net cycle power of 3 megawatts. Steam exits the reactor core at 100 bar, 520 degrees Celsius, and expands through the turbine to the condenser pressure of 1 bar. Saturated liquid exits the condenser and is pumped to the reactor pressure of 100 bar. Isentropic efficiencies of the turbine and pump are 81% and 78% respectively. cooling water enters the condenser at 15 degrees Celsius with a mass flow rate of 114.79 kilograms per second. So first we're going to determine the thermal efficiency, then the temperature of the cooling water exiting the condenser in degrees Celsius. So one little thing I'm going to do to my schematic is I'm going to put these dots, because these are technically rates, and I got this image from the Google machine. So I'd like it to match our notation. Okay, so we have properly dotted everything. So now let's just write in our givens. So P1 is 100 bar. T1 is 520 degrees Celsius. Okay, P2 is 1 bar. And we're going to number these parts of our condensers, 6 going out and 5 going in. So we're using cooling water, and T5 is going to be 15 degrees Celsius. The mass flow of our cooling water is 114.79 kilograms per second. Then P3 is going to equal P2, which is going to be 1 bar. And we're also told that we're at saturated liquid, so our quality at state 3 is 0. Okay. And we have some work going into the pump. And for state 4, we know that pressure at state 4 is equal to pressure at state 1, which is equal to 100 bar, since we're told this is the Rankine cycle. And this would, since we're dealing with a power plant, rather than a boiler, this would be a reactor. Let's just clarify that. Let's see. I think that's most of it. We're also given that W dot cycle is 3 megawatts. We're given that the efficiency, the isentropic efficiency of the turbine is 0.81. And we're given that the isentropic efficiency of the pump is 0.78. And we have to find the thermal efficiency, which is just eta. And we also need to find the temperature of the cooling water exiting the condenser, so that's T6. Okay, so hopefully you've taken all this down, and I'm going to open up a fresh sheet so I have more room, and let's go through and analyze each state. Okay, so for state 1, P1 is 100 bar, and T1 is 520 degrees Celsius. And we're dealing with water. And so you can go to your property tables in the book, and we can look up then H1. So practice going to your property tables and looking this up. I'm not going to pull it up just to save some time, but you'll find that the enthalpy at state 1 is going to be 3425.6 0.1 kilojoules per kilogram. And the entropy at state 1 is 6.6622 kilojoules per kilogram. Now, here's the thing. We have to also evaluate, so we evaluate each state as they stand, but then we also need to evaluate them as if they were isentropic processes, as if they were isentropic, so the ideal situation. So let's look at the ideal condition, so state 2s. So ideal for state 2. And for this, we're going through the turbine. So ideal for state 2, P2s is going to be the same as P2, which is going to be 1 bar. And so remember, with an isentropic process, so with this ideal, if this process were ideal, delta S is equal to 0. So then by default, we know that S2S is equal to S1 is equal to 6.6622 kilojoules per kilogram. Kelvin. Left off the Kelvin. Kelvin. There we go. And that means once we have found hold on, let me pause it. I'm going to pull up the property table so we can look at this piece together, since this is something we've never done before. So here we are looking at our property tables with respect to pressure. And so we know our pressure is 1 bar at state 2s. And so that tells us then also we need to figure out looking at our entropy. So we have our entropy for a quality of 0 and a quality of 1 here. And we know that our entropy is going to be 6.6622 kilojoules per kilogram Kelvin based on the entropy from state 1. So now, because we know that, we can go through and interpolate and solve for x2s. So we need to figure out what the quality is. And so when you after you find the quality, that you can then apply it to the enthalpy, and then we pick out our enthalpy. So I'm not going to go through interpolation with you. We have gone through interpolation together many, many times. So try it out on your own and make sure you get answers somewhat near mine. So the quality at x2s, once you interpolate, based on knowing the entropy here, is going to be 0.8849. And so that tells us that the enthalpy using this quality is going to be 2415.6 kilojoules per kilogram. Okay, so we have some information for state 2 and state 2s. So now let's look at state 2. So once again, P2 is 1 bar. And so now here's something new for you. We know we're going through, for process 1 to 2, we're going through the turbine. And in this problem, we're given the isentropic efficiency of the turbine. So we know that eta T is equal to H1 minus H2 divided by H1 minus H2s. So now we can go ahead and solve for H2. So H2 is going to be H1 minus eta T times H1 minus H2S, which is going to be equal to, then our H1 is 3425.1. Eta we were given as 0.81. H1 once again is 3425.1, and H2S is 2415.6. And these are all in kilojoules per kilogram. Okay, and so we get H2 is equal to 2607.4 kilojoules per kilogram. All right, so we're evaluating each state here. And just to remind us like where we're trying to go during this problem, keep in mind that the efficiency, is going to be work for the turbine. And since we're not given a mass, we're going to do this all on a mass flow basis. So that's for the turbine, minus W dot going in for the pump, so produced by the turbine, put into the system for the pump, divided by Q in. All right, and so we need to find W dot for the turbine, which is where we're trying to get now. And we need both H1 and H2 to get W dot for the turbine. And then we're going to have to go through state 3 and state 4 to figure out W dot going in for the pump. And then finally, we're going to have to find Q in, which is between 4 and 1, for the reactor to get eta. Okay, so now we have H2. So let's actually just put a little box around H1 because we're going to need that later, around H2. Okay, so now let's look at state 3 and state 4. So state 3, P3 is 1 bar. We know the quality is 0. And so in the table, we can look up. So we know P3 is 1 bar and the quality is 0. And so we get H is going to be 417.46. So H3 is going to be 417.46 kilojoules per kilogram. Okay, so let me put a little box around this. And let's also take down the specific volume now that we're looking at it. So V3 is going to be 0.00100432 meters cubed per kilogram. Okay, because we are going to need that for the efficiency of the pump. Now, let's look at state 4. So for state 4, we have P4 is 100 bar. And H4 is going to be then 430.7 kilojoules per kilogram. And remember, we're in the compressed tables here. So if you go to the compressed table, and we're at P4 is 100 bar. Okay, and H4 then is going to be 430.7. All right, so the temperature is going to be somewhere in between 100 and 140 degrees Celsius. And just a reminder, from state 3 to 4, we have isentropic compression. So that means S3 is equal to S4, which is going to be, so for quality of 0 and pressure of 1, let's just check this out. So for entropy, we're at 1.3026. And so if we go down to the compressed table, at 100 bar and 1.3026. All right, so then we have to do our interpolation to get the enthalpy. Okay, we're getting there, I promise. All right, so then we have interpolated and we get 430.7 kilojoules per kilogram. Now there's also another way you can figure this out using the isentropic efficiency. So let's do it both ways in this case because unless you're dealing with an ideal Rankine cycle, you're not going to have necessarily an isentropic process going from 3 to 4. So if we were then to use the given isentropic efficiency, okay, so this would be for an isentropic process, this H4, so you can also think of it as an H4S. So let me just like put a little S there, like just, you could think of it like that. But anyway, so that would be for an isentropic process, or another way we can solve for H4 would be using the isentropic efficiency of the pump, which is H4 is equal to H3 plus V3 times P4 minus P3, because for the pump, right, it's going to be isentropic work in over the actual work in. Okay, so then you divide by eta P. And we get out H4 is 430.7 kilojoules per kilogram. So a couple ways of trying that out. So V times delta P gives you the isentropic work in, and then this delta H, so this would be the ideal case on top, and then the delta H is the actual, but in this case we were dealing with the isentropic entropy condition, so we could have interpolated. So H4 is 430.7 either way. So let's put a box around it. Okay, finally, let's just look at state 5. So for state 5. Temperature T5 is 15 degrees Celsius, and we're dealing with a liquid. So the approximation there is that H5 is approximately H5F. So we could look at the liquid vapor tables, the saturation tables for X equals 0. And we just look up 15 degrees C, and we get 62.99 kilojoules per kilogram. Okay, so now finally we can just go through and figure the rest of the pieces out. So eta, the efficiency for our power plant, is going to be W dot T minus W dot P divided by Q dot in. And so this is going to be equal to H1 minus H2 for W dot T minus H4 minus H5 divided by Qn is H1 minus H4. And so you get 0.2687. For B, we have steady state because we're dealing with flow through the condenser. And so we have 0 is equal to H2 minus H3. So that's through the condenser, and the heat is being transferred to the cool water, which would be H5 minus H6. So H2 minus H3 is going to be equal to H6 minus H5. And so then we can go ahead and solve for H6. And H6 is going to be equal to H5 plus, oh, actually, let's not lose our m dots because these are different masses. I got ahead of myself with my assumptions. So this is m dot for the water going through the power plant, and this is m dot for our cool water. So those are two different streams, so they're different mass flows. So H6 is going to equal H5 plus m dot times H2 minus H3 divided by m dot C. And we can solve for our m dot. M dot is going to equal W dot cycle divided by W dot T minus W dot P. So this W dot cycle we were given was capital W. So it was total power for the cycle, and these in the denominator are the lowercase w dots, so those are on the mass basis. And so it's going to equal then W dot cycle over H1 minus H2 minus H4 minus H3. These are both 3s. Okay, so we end up getting that m dot is going to be 3.73 kilograms per second. I'm just going to change our color here so we can see it a little clearer. So H6, once we plug all our values in, is going to be 134.15 kilojoules per kilogram. And our temperature, then we can find by saying that H6 is going to be approximately equal to HF6. So we can go to our saturation tables for X equals 0, and we can look up that T6 is going to be about 32 degrees Celsius. Okay, Well, that is all for today. So I will see you next time.